I want to point out in terms of vertical and horizontal, and I'll just use the most famous vertical and horizontal lines, our y-axis and our x-axis. A horizontal line and a vertical line are perpendicular. They do meet at a right angle. Any line parallel to a vertical line is a vertical line. Any line parallel to a horizontal line is a horizontal line. Therefore, anything perpendicular to a horizontal line is a vertical line, and so on and so forth. Why am I pointing this out? Well, recall if I say wanted the vertical line through -2, +4. Remember my shortcuts. To get the equation of a vertical line, ask yourself what axis it strikes. And a vertical line would strike the x-axis. So a vertical line is x equals. And if we want it through this point, what's the x? -2. So the vertical line through -2, 4 is x equals -2. If I wanted same logic, if I wanted the horizontal line through the same point, a horizontal line strikes the y-axis. Therefore, it's y equals a number. In this case, y equals 4. We can add parallel and perpendicular stuff on top of that kind of problem. So if we have something, for instance, that passes through -2, -3, and is perpendicular to the y-axis. Think about this. If we're perpendicular to the y-axis, that means we are striking the y-axis. The y-axis is a vertical line. Perpendicular to that must be a horizontal line. A horizontal line strikes the y-axis. Y is -3. Another combination of this could be so I'm just changing things parallel to the x-axis. And if we think about it, there's our x and our y. If we are parallel to the x-axis, that means we're parallel to a horizontal line. We are some other horizontal line. And I changed everything, but we ended up back in the same spot. Horizontal lines strike the y-axis. So this is also y equals -3. Maybe one more. parallel to the y-axis? Well, if I am, here's the y-axis. If I'm parallel to the y-axis, I am also a vertical line. Vertical lines strike the x-axis, so x is -2. I want to talk about something called a piecewise defined function. And the key word here is piecewise. It's a function that's defined in pieces. It's cobbled together like a Frankenstein function. A little bit of this, a little bit of that. So you might have seen me previously draw things like this. If this is the graph, maybe something like that. And while this couldn't be one thing, between here and here, this is a piece of some larger line. And then between here and here, that's a piece of some larger line. And between here and here, that's a piece of some larger line. And between here and here, and then there through there, it's this side of that line. So if we cobbled together these 1, 2, 3, 4, 5 things and put restrictions on the x values we were looking at, we could get this function written in numbers and letters. So imagine this was our function, f of x equals, and then this is not a face. It looks like a face. Hello. For someone who can't draw, that's a pretty nice face. There we go. Not what I was drawing. We're doing math. We're not drawing. That's a left brace. It's not going to have a right brace. So this is all this big symbol here, this left brace, like we would see on a set, just the left one, is going to group together a bunch of different functions, different conditions. This will be the function we're going to look at. We have 3 functions put together. F of x equals -x minus 1. F of x equals -3. F of x equals the square root of x minus 2. But remember, just like that one I drew, between different values of x, we'll have one of these different pieces. So the function is equal to -x minus 1 for all x less than -1. And the function is equal to -3 for all x between -1 and 2, equal to -1, but not equal to 2. And f of x equals the square root of x minus 2 for x greater than or equal to 2. So my first question for you is, what is f of -3? Well, normally to find f of -3, we plug -3 into the function. But which one do we plug it into? Well, we look at the rule. F of -3 means x. Means, there we go. Means x is -3. Well, -3 isn't greater than or equal to 2. -3 isn't between -1 and 2. -3 is less than -1. That means for f of -3, we put it in this one. Instead of -x minus 1, we have -3 minus 1, two negative signs, because we are replacing the x with the entire -3. When I write this out, when I plug things in, I like to just replace my x's with parentheses first to make sure that I get the right number of outside minuses. And then I plug my -3 in afterwards. And then I evaluate. The opposite of -3 is +3. 3 minus 1 is 2. So f of -3 in this piecewise defined function would be +2. Same function. This time, f of -1. Well, we can rule out the third one right away. -1 is not greater than or equal to 2. But are we going to use the first one again, or are we going to use the second one? Well, -1 is not less than itself. So we would have to look for the or equal to here. So if x is equal to -1, like here, it's going to fall on the second one. And for all x values here, including this one, the function is equal to -3. Nothing else to do there. It's just equal to -3. Next up, let's look at f of 2. 2 is greater than or equal to 2. So I'm plugging in 2 minus 2 under the radical, which is the square root of 0, which is 0. So f of 2 is 0. Finally, for this function, let's take a look at f of 6. Where does this fall? 6 is greater than or equal to 2. So it's the radical again. Radical 6 minus 2 is radical 4. And since we're just evaluating the symbol, that is the positive version only. F of 6 is 2. Graphing one of these should be something that we are comfortable with. Let's take a look at the following. F of x equals f of x equals, this is negative 3x for x less than 1, and just negative 3 for x greater than or equal to 1. The first step in graphing a piecewise function is going to be to look at where we're splitting our x values. So here, at x equals 1, we would draw a dotted line, vertical, straight through the x value. Now to the left, we'll have one graph. To the right, we'll have the other. But we get two pieces of information from this dotted line itself. That information is going to come from these two lines. The one that has the or equal to, that's going to be our filled in circle. It's going to include that point. The one that's just less than or greater than, that's going to be our open circle. To figure out where we're going to put our open circle, our closed circle, our filled in point, our open point, we're going to plug the x value in. Yes, I know this is the one that says equal, but we're still going to do both. The one that says equal is going to be the filled in one. That is where the graph will exist there. But we still need to know where the open circle is. That's why we plug it in here as well. So if we plug in 1 to the first one, the open circle, if we plug 1 in, negative 3 times positive 1 is negative 3. So we will have our open circle on the x value of 1 at negative 3. If I go to the second one, well, my filled in circle is also at negative 3, because for all x values greater than or equal to 1, I'm at negative 3. So I get to fill in my open circle. It's the same point. That means this graph's going to be continuous. It's not going to jump to another point to continue off. And actually, for all x greater than 1, so for 2, 3, 4, 5, 6, this graph is just f of x equals negative 3, y equals negative 3. Why do we need to know how to graph lines? Well, part of this is knowing how to graph lines. We did this in the last unit. So what about this side of the dotted line? Well, over on this side, we're going to have y equals negative 3x. Y equals mx plus b. We know how to graph that. So this is like y equals negative 3x plus 0. That means the y-intercept is 0. The y-intercept's on this side of the line, this side of the graph, the side we need. That's fantastic. Otherwise, we couldn't just plot the y-intercept. We would have to use the slope to count off another point. What would the slope have been? The slope is -3, which is -3 over 1, or 3 over -1. Remember how I kept pointing out 2 different ways to do that? Why? Well, this would be down and right. But from this point, down and right, we don't want that side of the line. We want it on the other side. So we have to know that we could also go up 3, left 1 to get our next point. So either way, from the y-intercept, if it's on the right side, or from the slope, we get our second point. And we draw our graph off. So this is that graph. What's that? You want one more? Okay, happy to oblige. Let's do one more. This time I'm going to graph f of x equals x plus 3 for x less than -1, x squared for -1 less than or equal to x less than 2. Okay, where are we splitting? Where are we splitting our x values? -1, +2. -1, +2. -1, we're going to have an open circle and a closed circle because we have just a straight less than -1. We also have an or equal to. 2, we're going to have an open circle because we have a less than 2, but we don't have another one with 2. So here we'll have an open and a closed. Here, we're just going to have an open, just an open for 2. -1, we'll have an open and a closed. Let's find these values. So for -1, let's do the open first. That's here. -1 plugged into x plus 3 would be -1 plus 3 would be +2. So on this x -1 at +2, there is an open circle. For the filled in circle at -1, we would go here. -1 squared is +1. So there would be a filled in circle at 1. Over here at 2, For the open circle, we would plug in 2 squared is 4, 3, 4. It's an open circle up there. Now, in between is fun. We're going to connect from the closed circle of 1 to the open circle at 2. And the graph is x squared. We know this graph. Point at 0, 0 because it's not moved up, down, left, right any. It would connect where it's equal to -1 over here. And when we're equal on the -1 for the x, that was at 1. Over here on the right, it's going to connect at 2 to an open circle. And that was at 2, 4. We have nothing at all off to the right. Off to the left, off the open circle, we have a graph y equals x plus 3. The y-intercept would be 3, 1, 2, 3, but it's in the wrong part. This x plus 3 has to be the graph over here on the left, so we can't use the y-intercept. But it has a slope of 1, which is up 1, right 1, wrong direction, or down 1, left 1. So this graph here would be this piecewise function. Now, the fact that a piecewise function is a function means that when we graph it, we will not have 2 lines in the same spot because that fails the vertical line test. A piecewise function, being a function, is just going to be a bunch of different graphs that may or may not connect at the barriers. If it doesn't connect at the barrier, then it's not continuous. If it does connect at the barrier, it's called continuous. But notice if there are 2 spots, one's going to be an open circle, one is going to be a filled in circle. Why? Because if they were both filled in, it wouldn't be a function. It would fail the vertical line test. So in order to be able to graph a piecewise function, you have to be able to graph lines. Before we even get into the piecewise function of it all, I want to say we know how to graph both of these things. We know how to graph y equals -3x minus 1. We know how to graph y equals -x plus 1. So I'm going to graph them both. Y equals -3x minus 1. If we had this graph, would have a y-intercept of -1. So that would be a point. And then a slope of -3. Down 3, right 1. Or up 3, left 1. Either way, we would have this line here. Now, what this means, f of x equals -3x minus 1, if x is less than -1, that means that at this -1 barrier, where we're split less than and greater than or equal, when x is less than -1, we have this graph. So we have this graph everywhere to the left of this dotted line. Everywhere that the graph is less than -1. Where it's greater than or equal, we don't care about any of that. We only care where it's less than -1. And since it's not or equal to, that's a filled in circle. Now, how could we get this without graphing the entire line? Well, instead of the y-intercept, because that's not going to be useful for us, the y-axis isn't even part of the things to the left of the line. The line's at -1. If we plug -1 in, y equals -3 times -1 minus 1. Y equals +3 minus 1. Y equals 2. When x is -1, here at y equals 2, that's where our filled in circle would be. And then we build off of it. How would we continue to draw the line? Well, the slope is -3. Down and right, that's the wrong way. That's the wrong side of the dotted line. So we would go up and left. -3 is -3 over 1. But it's also 3 over -1. So if down and right doesn't work out, we could go up and left. Up 3, left 1. Up 3, left 1. And there's our next point that we would drive through. There we go. So what about the right side? Well, the right side would be the graph of y equals -x plus 1. We know how to graph this. It's a y-intercept of 1 and a slope of -1. Down 1, right 1, or up 1, right 1, or up 1, left 1, sorry. -1 for a slope is -1 over 1, or 1 over -1. Down and right, or up and left. Notice up and left is going to fill that point in. So it's continuous. But the graph looks like that. So imagine we had the full graph. It would be like this. But since we're only interested to the right of the dotted line, everything to the left would get erased. So we wouldn't have however the line continues, because none of this matters to the piecewise function. We only want the part where x is greater than or equal to -1, where we are to the right or at -1. So hopefully, now that I've explained it this way, that this is two full graphs that we're cutting at -1 and we're putting together so that the right side of -1 is this one and the left side of -1 is this one. Hopefully, if you can grasp that, then the method I showed in the last lecture for graphing piecewise functions will make more sense. So, how would I do this from scratch without thinking of it being two separate lines? Well, I make it all about the partition points. In this case, we only have one at -1. And I put a dotted line in there. And then I find all the filled in or open circles, endpoints on this line. Since this dotted line is -1, I put that value in for x in both of the functions. When x is less than -1, I use the top. So the top one is going to be an open circle because it's not or equal to. So top, that's going to be an open at -1. So for -3x minus 1, I put -1 in, and I get 2. So when y is 2, I have a filled in circle here. X is -1, y is 2. Now for the bottom. Since it's x greater than or equal to, this one is filled in. And I'm going to test x equals -1 in -x plus 1. That's the opposite of -1 plus 1, which is +1 plus 1, which is 2. So here I also have the y value of 2. If it was anywhere else, it would just be a filled in circle, but since it's in the same spot, that means we have the same point here. So the filled in circle from the bottom is actually filling in the open circle from the top. Now that we have all of the filled in or open circles on the dotted line, we go left and we go right. We do the correct slopes off of the correct points. So for -3x minus 1, that's a slope of -3. -3 is either -3 over +1 or +3 over -1. So either down and right or up and left. Since we want to the left of this point, then down and right, that's not going to do. We need up and left. Up 3, left 1. We can go again. Up 3, left 1. We draw our line, but it stops at this dotted line. If it was the full y equals 3x minus 1, it would be the whole thing. Now here, Negative x plus 1 has a slope of negative 1, which is either negative 1 over positive 1 or 1 over negative 1. So it's either down and right, or it is up and left. Since we want to go to the right, we have the down and right one. Down 1, right 1. Down 1, right 1. Down 1, right 1. Down 1, right 1. So off to the right, we have this line with the slope of negative 1. So we have a slope of negative 3 until we hit this barrier, and then it changes to the one that has the slope of negative 1. But if it was the whole line, it would just keep going. We don't care about the stuff to the left. This is not a straight line. This isn't one of my drawings that went awry. This is actually supposed to look like, instead of a straight line, a bent line. Slope of negative 3, slope of negative 1. Hopefully that helps clarify piecewise functions. Average rate of change. Now, the average rate of change is basically the slope formula. Recall the slope formula, m equals y2 minus y1 over x2 minus x1. And that's how we find the slope of a line between 2 points, x1, y1, and x2, y2. If we wrote these points in function form, where instead of y, it's f of x, the point x1, y1 would have x1 as the x coordinate, but the y coordinate would be f of x1. In other words, the output of the function when the input is x1. And instead of x2, y2, we would have x2, f of x2. X coordinate of x2, y coordinate, the output of the function when the input is x2. These mean exactly the same thing, these two sets of points. So, another way of looking for the slope formula is f of x2 minus f of x1 over x2 minus x1, but it's still the slope. And we're going to call this the average rate of change. So what is this? What does it mean? What do we do with it? Well, we just talked about piecewise functions, and when we were doing the piecewise functions, we graphed two linear functions, two lines. Now, lines have slope, and we used the slope of those lines. But not all graphs are lines. We've seen the different shapes. Parabolas, for instance. A parabola doesn't have a slope. There's not a constant up and over, up and over, up and over the whole way through. But if we picked 2 points on the parabola and drew a line through them, that line would have a slope. And we would call the slope of that line the average rate of change from this point to that point. And we'd use the x values. So it's just the slope of the line through 2 points. And by the way, a line through 2 points is called a secant line. So secant line is just a fancy name for line through 2 points. If the line only went and touched at 1 point, it would be called a tangent line. That's an instantaneous rate of change. We're not going to get into that. We're just talking about average rates of change, the slope of a line through 2 points, the slope of a secant line. So let's hope that all my technology works here, because I do have a visual aid for once. I'm not going to rely on me drawing something out. So let's just give me 1 second. Document camera. And that's all funky because of the totally real room I'm in that's not a green screen. Let me take care of that. Okay, so what we have here is a graph of blood alcohol concentration versus time. The x-axis is number of hours. The y-axis is the blood alcohol concentration. So if we were to find, for instance, the average rate of change of blood alcohol level from x equals 0 to x equals 1. All we'd be doing is finding the slope of the line through those 2 points. So I made it a little bigger there. From x1 equals 0 to x2 equals 1, let's find the average rate of change of the blood alcohol level. So our formula is just the slope formula. But instead of y2, we're going to call it f of x2. Instead of y1, we're going to call it f of x1 over x2 minus x1. Bottom part's easy. That's 1 minus 0. That's 1. Now on the top, we would want the function outputs, the y values for each of these x's. So x2 was 1. And we can see right there, we have the point 1, 0.06. So when x is 1, the y value is 0.06. When x is 0, we have the point 0, 0. When x is 0, y is 0. So that's 0.06 over 1. From 0 to 1, the average rate of change of the blood alcohol level would be 0.06. Now that wouldn't be 6%, that would be 0.06%. And why do we know it's a percent? Because the graph tells us blood alcohol concentration, the units are percent. What does this mean? It means during the first hour, from t equals 0 to 1 hour, the blood alcohol concentration rose by an average of 0.06% per hour. Percent per hour. Y's over X's per hour. Because the top, the Y coordinates were in percents, and the X coordinates along the bottom were in hours. Percent over hour is literally percent per hour. Let's do it again. Let's find the average rate of change, this time from x1 equals 1 to x2 equals 2. So f of x2 minus f of x1, which is the same as y2 minus y1, over x2 minus x1, over 2 minus 1. So this one's over 1 again. 1 what? 1 hour. On top, when x is 2, we have the point 2, 0.09. When x was 1, it's the same point as before, 1, 0.06. When we subtract, we get 0.03. And that's percent, not 3%, it's 0.03%. So the average rate of change from x1 equals 1 to x2 equals 2 is 0.03% per hour. So it's less of an increase the second hour than it was the first hour. First hour was an average of 0.06%, second hour 0.03%. And we can see that the lines are getting shallower. The slope is getting smaller. So the average rate of change, percent per hour, is getting shallower. It's getting smaller. Let's do one more. Let's go from x1 equals 1. Nope, sorry. x1 equals 2.5 to x2 equals 8. So these points are on our graph as well. We'll set up f of x2 minus f of x1 over x2 minus x1. x2 is 8. x1 is 2.5. That means here on the bottom we have 5.5. 8 minus 2.5. The directions on this one, by the way, say round to 3 decimal places. We might need that information since we're dividing by something that's not 1 this time. When x is 8 for x2, we have the point 8, 0.02. When x is 2.5, we have a y function output of 0.095. That top number is going to be negative. 0.02 is a smaller decimal than 0.095. I don't want to do this by hand. You don't have to either. Calculator. 0.02 minus 0.095 equals negative 0.075. Negative divided by positive is negative. 0.075 divided by 5.5 is that big long monstrosity. Rounding it to 3 decimal places, 0.01, and that 3 is going to round up to a 4. So negative 0.014, and again, tops are percents, bottoms are hours. So this is negative 0.014% per hour. What does that mean? It means on average, from the 2.5 hour mark to the 8 hour mark, if you imagine the slope of the line between those 2 points, on average, we are decreasing 0.014% per hour. You're getting less drunk as time goes on after about 2.5 hours. And in that span of time, that 5.5 hours, on average, you're getting 0.014% less drunk per hour. Okay. Let's see if I can get us all back to normal now. Okay. Looks back to normal to me. Hi. It's been a minute.